Alright, so next. Alright, model selection. So the problem with model selection is to given data, choose estimators or model if the estimators are underpinned by a probabilistic model, and to choose the parameters. So to relate to the previous tutorial, I can have a set of models and also a set of priors. And how do I choose, given my data, which one I should use, which one fits the data best? So this is a very, very wide problem in statistics. And we're only going to see it through the eyes of the machine learning. You could have other answers. All right, so as we have seen, the different estimators expose a score method that is related to the problem they solve, that you can apply on new data, and basically the bigger the score, the better the estimators perform. So I'm not going to run this example, but you can just split out data, train a test, and apply a score to it. So to get a better estimate of the prediction score, rather than simply split out the data, train and test, we can do several splits. So one way of doing this is to split the data in 10 folds. For instance, split it evenly in 10, and each time train on none of the folds and test on the left-out fold. So that gives us 10 sets of train and test, and then we can average out the scores. So we can simply do that. This is code that's actually a bit convoluted to write. Got 2 hours left. Okay, so I'm going to skip typing this code. That's convoluted because we're not going to do it anymore. Anyhow. So far I've been forcing you to split the training and the tests manually. What we're going to see here is that looks like it can do this for you. So if we want to split in folds, we can take the data, the X data, the Y data, split it in a list of 10 folds. Each time, go through this, leave out. So we want to leave out a test fold. Concatenate the other ones in a train fold. So we do this for X and Y, and then train on the test set. Train on the train set, test on the test sets, and we do a list of scores and all this, and then we have the different scores on each fold, how they vary, and then we can, for instance, average them out. So we can see that prediction accuracy varies a bit, but not too much. If it's varying widely, we're probably not splitting the folds in uniformly distributed, identically distributed data. For instance, if we've got sorted data, then we might have in the train set only 2 classes, and in the test set a third class. We're in trouble. So if we see wide variation across folds, we're probably not doing things right. So this, by the way, is called K-fold cross-validation in the jargon of machine learning, or V-fold cross-validation in the jargon of statistics. All right, so as I said, we're not going to type this. This is tedious to type. We happen to have cross-validation generators. So there is a submodule of Scikit-learn that is called cross-val, or cross-validation, and we can import from it. And it exposes a set of different objects, and one of them is K-fold. So we can create a K-fold object. So it takes N, which is the number of observations, and K, which is the number of folds. So we want to split a 6 observation in 3 folds. So what this object is a Python generator. So it means you can iterate through it, and when you iterate through it, it's going to give you mask, NumPy arrays of train and test. So as I've asked for threefold, it's going to give me, I can iterate through it 3 times, and each time I'm going to have a different mask of train and test. So just to get an intuition, so I iterate through it, and each time I get a train mask and a test mask, and then I can print them out. Right. So as we can see, in the first fold, we're leaving out from the train the 2 first observations, and they're included in the test. Second fold, we're leaving out the 2 in the middle, and they're included in the test. And third fold, we're leaving out the 2 last. So in general, we can do this for as many samples and as many folds as we want.
Is there a restriction on the, does one have to divide the other? In other words, you have 2 and 6, and 2 divides 6.
No, there's not. No, there's not. That's one of the corner cases that the Scikit deals with. Yeah, because that code gets hardly ugly to deal with. No, there's not, which means that you're not going to have the same number of observations in the folds, which is fine. And actually, we could debate on how you weight the folds during the mean when you're doing the mean, and remind me to answer this question when I see how we get an average score across folds. So then we can look at cross-validation across the folds using this k-fold object. I've added another score here and not there. So in general, in this Scikit, we try to be really consistent with the names, and between words, we try to put underscores. That's the rule. So we can just do a list comprehension. And we're going to be splitting our data set in train and test using fancy indexing, NumPy fancy indexing. So each time we fit on the train and we test on the test. So we're getting train and test from the k-fold object. And it can work. Underscore. That's because I tried to jump ahead and not do the first example. That's what you get. Hooray. All right, what's wrong? That's pretty bad prediction. Oh, the k-fold object was created for 6 samples. We actually have much more than 6 samples. So we're just taking the 3 first of our data set. This is not the right way to do it. Let's fit it. It's taking a little while. And there we go. Whoa. Really poor prediction. Something's wrong. Hmm. Oh, wow. Well, I'm going to move along. It's probably some parameter that was set different when I ran the example, which does tell me that I should always doc test my documentation. All right, anyhow. So, we'll be doing this kind of stuff a lot, basically, to set parameters. Given an estimator, it almost always has a parameter. To set parameters, it can have its own heuristic to set parameters, but really, in practice, most often, the way that actually works to set the parameter, unless you have strong knowledge of what is in your data, is to set it with cross-validation. So basically, given an estimator, I'm going to do k-fold cross-validation or some other kind of cross-validation to choose the parameter that maximizes prediction. So for this, we have, to compute the score, the cross-validated score of an estimator, we have a function called cross-val score in the cross-val module that takes an estimator, the data, so x and y. Optionally, this is not compulsory, but optionally, a cross-validation generator, and something that allows you to use all your CPUs. So there's this optional parameter and jobs that tells it how much CPU you want to use on your computer. Under the hood, it's using the multiprocessing library, and if I put it to -1, I'm just telling it, use all the CPUs. So this is actually trivial parallelization. It just fits on the different CPUs. And we're getting crappy scores, just as we were before, because it's the pure exact same code, except that it includes, you don't have to specify the CV, so then it will instantiate it for you, and it does all the dispatching.
Hey, Kyle, why didn't you have to reset the k-fold generator? The k-fold generator?
Because it's not really a generator.
Oh, okay.
We started with generators, and then we had to preset them all the time, so it's
Okay. Smarter than
yeah, it is an object with a nature method. It should expose a lane. We didn't want to implement a special object, and then it was just too tedious to reset them all the time. So basically, there are only two kinds of objects in the Scikit-learn currently. Well, two kinds that you have to use. One is the estimator, the other is the cross-validation object. And the cross-validation object behaves very much like a generator. All right. So, we've seen the k-fold estimator that just splits in k different folds. So, splits the data in k, trains on k minus one of them, and tests on the left out. A common problem is that the data may not be ID distributed. Therefore, if I split, if I'm doing a classification problem, I could have only one class in my left out data. So we've seen this with the iris data set. So if you're with in a classification problem, you can do what's called stratified, what we call stratified k-fold is it divides in folds with approximately balanced class across the folds. So it looks at the y variable to balance it across the fold. So it looks a bit like k-fold, except it takes the y data, the y variable, because it needs it to split out the fold. So as a side note, the cross-val score function here looks at the estimator you're giving it. And if it is a classifier, we'll use a stratified k-fold by default. So it tries to do the right thing. We can leave one out. So we're leaving out one observation. This is not really something you should be using most of the time because you have only one sample to test your prediction power. So you're going to get a lot of noise in your prediction power. So this is not a good model selection criteria. We can leave one label out. So this is in the case with real data. Most often, the problem is not as simple as X and Y data. You might have a set of subjects that have some have diseases, some don't, but you may have several measurements across one country, for instance, and you may want to leave out one country. The question being, if I learn a predictive model in one country, can I transfer it to another country? So then you're going to have a label vector, which is going to give a number per country, and then you can do leave one label out, which would be leave one country out. So this is one way. Basically, you can encode whatever you want in the label vector, and this is one way we use it on real data that has a bit more structure than just ID observations. All right, so now we're going to do an exercise. We're going to take the digits data set, and we're going to use a support vector classifier on it with an RVF kernel. And as we've seen, choosing the right gamma on the RVF kernel is critical. So you can use a cross-val score on a logarithmic grid of points from 10 to the minus 6 to 10 to the minus 1 and draw a plot about the prediction power as a function of gamma. And the plot should look approximately like this. And I can't spell exercise. Alright, so one way to do this is just to create a scores list that we're going to append to. I'm also going to store the standard deviation. Then I can iterate in my gammas. Each time I can set the gamma parameter of the SVC value, I can get the scores with this gamma using my cross-val score function. I'm going to use my two CPUs, and I'm going to append the mean to my scores. List. And I'm going to store also the standard deviation. And I've just made a typo above, so I'm going to go through the typos. This is just computing. All right, that looks approximately right. We can plot it. We're going to plot it using our scale. Right. So, too small gammas don't work, too big gammas don't work. There is a range where gamma works reasonably well. You'd just like to take the optimal value in there. All right, any questions on that? Okay, so basically using cross-validation, we can tune the parameters of an estimator given data. So for instance, if I have a sparse estimator, if I know how sparse my ground truth is, I can directly set the value of alpha that controls the sparsity. The problem is, most of the time I don't know. And even if I know, I could be wrong, because most of the time I have a noisy observation of my real underlying truth, and my limited data may not support all my claims. So there's what people call the grid search, which is, I'm going to do a brutal search over a grid of parameters and choose the parameter that maximizes my cross-validated score. So if I have only one parameter, my grid is a 1D grid. If I have a set of parameters, then I'm going to build an MD grid and extension this. So obviously, if you were trying to set a lot of parameters like this gets quickly very expensive. You don't want to be setting 10 parameters. Besides, you might probably be overfitting. You're probably going to learn in your parameters. You're going to learn what looks like a fine description of your data, but unless you have a lot of data, what you're just going to be learning is fitting the noise. So the Scikit-learn exposes an object that's called a grid search CV. CV stands for cross-validation. That does this for you. So basically, you instantiate it, given an estimator, and a grid of parameter. And when you call fit on it, it will do the cross-validation for you. It will take the data, split it according to a cross-validation object, fit the estimator that you gave it on each of the folds for each of the parameters in the grid, take the parameter that maximizes the score, stick it as a parameter to the estimator, fit the estimator on all the data, return the answer. Big black box. On top of this, it can do this on all your CPUs. My workstation in my work has 12 CPUs. So, I'm biased. Right, so let's try and use it. So it takes an estimator and a pairing grade. So it's a dictionary of name of the parameter you want to set on the estimator and list the value it can take. So if I'm giving it several parameters, it will just do the cross product of the grids. And each time you're getting bigger and bigger grids. So you can set as many parameters as you want doing this. I don't advise you to do it. So here I'm letting gamma, the gamma parameter of the support vector classifier, vary in the gammas. And I'm using all the jobs. And I'm going to fit, and just once again I'm going to do what I have said I wouldn't be doing, is I will manually leave out a bit of data. I need to call it fit method. So it's important to understand that when you call fit, it will do a cross-validation. That was false. So it exposes a set of learned attributes. One of it is best score. So it's done the grid, and the best score in the grid was 0.99. So we can go back and see if it matches what we had here. It does match what we had here. So it has a best estimator, where we can see the parameters that it has taken for the estimator. So it's given us a gamma of 5 10 to the minus 4. So it's lying here. Seems reasonable. It didn't choose the very exact same gamma here because we didn't give it the full data. We left out a bit of data. So that's, once again, going back to what I was saying, that if you're going to learn very precise values for your media parameters, you probably shouldn't trust them. And we can see how it scores on left out data. So it's being fitted. So I can try to use score on the data that I didn't use for fitting. So I get 0.96 prediction. So what we see is that the best score on the training set is higher than the best score on the left-hand set. Right. This can be understood, for instance, by the fact that the gamma, the optimal gamma on the training set is not exactly the same as on the test set. But that's all you can learn from your data. So if we want to, so we could be using a cross-val score to estimate the score of this estimator by doing all the folds. Here I've done manually, I've done only one fold, I've taken only part of the data. The reason I didn't do this is I wanted to save computing time. But if we just use cross-val score on this estimator, we're going to get cross-validation, and inside the cross-validation, we're going to get cross-validation to set the parameters. In machine learning, this is called nested cross-validation. If you want to estimate the prediction accuracy of an estimator that is itself set by cross-validation, it is important that you do this. Elsewhere, you will be overestimating your prediction accuracy. And so, if you just use the scikit in the way it's designed to be used, which is simply using the score function, the cross-val score, you are naturally doing this. You just have two cross-validation loop going behind the hood. All right. So one technical remark is you cannot nest different objects that use multiprocessing. So you can't run in parallel an object inside an object in parallel. This is just a limitation of the way we're using the multiprocessing library. It's technical, but it's it's just going to crash on you with a horrible trace back. Another limitation to have in mind is it's just harder to do debugging when you're doing in parallel. You can't, for instance, do introspection. So if things start crashing, just switch job to 1, debug, and then switch it back to -1. All right, so we've seen the grid search. It's a bit of a brutal approach. Works well, but sometimes you can do better. If you know the algorithm, you may know that you could use exploit properties of the algorithm to do the fit while varying the parameters in a quicker way or across the folds in a quicker way. This is why for some objects, for instance the lasso, there is a corresponding lasso CV object, which is cross-validated lasso that sets its alpha parameter by cross-validation. Internally, it uses, actually it simply uses 1 restarts, just a trick to speed up things. But if there is a CV object, chances are you should be using it rather than the grid search. So if we import the linear model, we can create a lasso object using lasso CV, and the nice thing is we don't have to set its alpha. It will choose it itself. So then we can use the diabetes data set, which is a regression problem, to try it out. And I do believe it also takes an job parameter. Okay, I was wrong. That response. Okay, so then we can have a look at the alpha parameter it shows, which is that. Interestingly, I don't get the same thing than in my example. Right? So basically, if you have an estimator and you find an estimator with CV at the end, you can use it to set some parameters by cross-validation. I'll just give the answer to the exercise. But we can have a look at the bonus question. So we've just found the optimal alpha by cross-validation on the diabetes data sets. The question is, how can you trust this? That's an helpful question. Alright, so there are several ways of tackling this. We could do what we've been doing before, which is just do cross-validation for each alpha, and then have a look at the curve and see if it flattens out or not. It just happens that this lasso CV object, if you look at the parameters, it the attributes it has. It's got an MAC path underscore. So to understand this, so first we can look at, so it's an underscore variable, so it's being estimated from the data. It's 100 by 3. So there's no way you can guess what it is. So it also has an alphas parameter, which is an array of shape 100. So MSE stands for mean square error. So this is pretty much the mean square error on each fold. It's done a 3-fold. How can we know it did a 3-fold? We cannot. Well, we probably can't by looking at the documentation. It takes a CV object and it doesn't say the default. Okay. So we just have to look at the code if we really want to do this. By the way, you all know how to look at code in IPython. You do double question mark, you can look at the code. So, whatever. So it's done a 3-fold cross-validation on each of these alphas. And lasso.msc path gives the mean square error on each of these alphas. So then we can take the mean across the folds. No, wrong way. And we can plot this as a function of alpha. All right? So error, smaller is better. So this tells us that pretty much the model works best for no regularization, almost. And if we tweak a bit, are great. So what this tells us also is that we've probably not gone far enough with the alpha grade. Right? We've not seen any saturation. And the people I work with in machine learning, they want what they call a happy curve. A happy curve, if bigger is better, starts from low, goes to high, goes back to low. Your model is the maximum. This is not a happy curve. So can we get a happy curve? So if we look at the lasso CV object and the arguments it takes, you can give it explicitly the alphas on which you want to fit. Well, so clearly we didn't go low enough. So if we look at the alphas that we used so far, yeah, they went as low as 2 10 to the minus 3. So let's go much lower. So we're going to create our own alphas. We go from -1 to, well, 10 to the minus 1 to 10 to the minus 6 and fit 100 values. So we're going to create, well, we could actually just simply stick these in the alpha parameter of the lasso. Then we're going to refit this one. That was fast. Something's wrong here. All right. Well, let's for instance take this. It seems that the lasso object doesn't like having its alpha parameter changed. Well, the lasso CV object. And then we can fit it. well, I don't know what's going on here, but that's pretty bug. So we're going to move on. So if you look actually at how I had coded this in the solution, I had not used the object. I had done it with the loop. And the solution looked like that. So we can see that for alpha around 10 to the minus 2 there is a bump. But what we cannot see here is that it's actually a really small bump. And prediction is never really good. So there is an optimum alpha that is non-zero, but really it could be lying anywhere from here to 0. All right. Any questions on model selection? Right, unsupervised learning. So unsupervised learning is when you don't have y. You have x but not y. So one way of seeing this is that you're going to be looking for some meaningful or interesting representation of your data. So I'm going to be talking about, first I'm going to be talking about clustering. So how can you group observations together? So you're given observations, you have no labeling on them, how can you group them together? So for instance, if we had the iris data set, somebody had told us, well, there are 3 kinds of irises in there, but had not given us y. Can we recover y? So clustering in general, there are many ways. There are many criteria, goodness of fit criteria that you can have with clustering. It's not like a regression where they're mostly equivalent. So therefore there are many algorithms. And the simplest one is the k-mean algorithm. So I'm just going to recompile this so that I don't have the figure in the way. Alright, so this is running k-means on the iris data set. So it has 3 classes and it is described by 4 features. So I've plotted only 3 features of the 4. And so I've told k-means that I wanted 3 clusters. And I found the different clusters that minimize an inertian criteria. So basically minimize the square distance to each of their center. And so we can run this by importing. So we import a cluster from Scikit-learn. So we have our iris data set. Let's pretend we don't have the y. So we can create a k-means object using cluster.k-means. And we tell it that we want 3 clusters. We can fit it to the data. So this time fits takes only x and no y. Right, so it ran. And then we can have a look at the labels. Let's plot one label out of 10. So labels are which class labels. So k-means has learned 3 clusters, and the label is to which cluster out of the 3 does each observation belong to. So now we happen to have labels for this data that comes from our data sets. So we can try to compare the labels, the real labels, to the one that were found by clustering. Right, so what do we see? You see that there is some consistency. First, in clustering, the class label is random. What was labeled as 0 in my ground truth was labeled as 1 by the clustering algorithm. Second, we get things that are errors. But there is some consistency. Alright, so this is dangerous. I see a lot of people using clustering instead of using classification. Nothing in the clustering algorithm is telling it needs to look like the ground truth label. So if you have labels, you should be using them. If you have a supervised, this is general, if you have a supervised problem, chances are that if you're doing unsupervised on it, and only unsupervised, you're doing something wrong. So, another warning, clustering is a nil-post problem. So, this is the kind of stuff you can run in with clustering. So this is the very exact same code that I've shown you, except it's fallen in local minimum. Clustering is a non-convex optimization problem, and you will fall in local minimums. So this looks really ugly, by the way. You wonder how an algorithm can fall there. So we do play a lot of tricks in the Scikit-learn to avoid this. We do things like, if you look at the k-means object, it's got parameters like n in it. So we initialize it 10 times, and we take the one that has the best inertia criteria. It's got a clever initialization strategy. I had to turn these features off to get such an ugly example. But the more complex the data set, the more chances you are to fall in the local minimum. Basically, when you got big data set, you have absolutely no guarantee to recover a ground truth. That's something to keep in mind. Another thing to keep in mind is that choosing the right number of clusters, if you really don't know anything on your underlying data, is a very hard problem. And if you choose the wrong number of clusters, you're going to get meaningless results. And this was just to compare, and this is not going to show. Well, it was just to compare with the underlying ground truth, and actually k-means did pretty good on this data set. They made a few errors, but not much. But I still do want to stress the disclaimers. I'm not saying it's not useful, it's very useful, it's just don't overinterpret. I see people publishing things with clustering that I believe are initialization dependent. Alright, so here's an application. So clustering can be seen as a way of compressing the information. Instead of continuous representation, I can cluster this and use only, report only the class in which I am. So for instance, we can do this to posterize an image. So for those who've been playing with Photoshop, posterizing an image is converting it to a finite set of query level. So let's play a bit with Lena. We haven't played with Lena so far. That's it. For those who don't know, Lena Here's the name. So she is 512 by 512 grayscale image. And we can consider this as a random variable. Just flatten the image and then try to do clustering on it to find if we can find a level of gray to approximate this. So the first thing that we're going to have to do is to flatten it. Well, not exactly flatten. We want n observation by n features, n sample by feature array. So there's only one feature, so it's flattened but 2D. So we can, let's reshape -1, 1. Alright, so we've got 512 by 512 and 1. So then we can instantiate a k-means object. And I'm just going to take 5 levels of gray. And so I'm actually initializing it only 2 times because I want it to be fast. And I can fit it to the data. Alright, so then we can look at the parameters it has estimated. So we have labels. So it means for each pixel of Lena, which label does it belong to? And we also have cluster center. So it's what's the value of the center of this cluster. So what's pretty much the mean value in these labels. So I'm going to retrieve the values. I'm going to retrieve the labels. Then I'm going to assign, you're going to go away. Actually, the values, I need to squeeze this because they're a 2D array. Then I'm going to create a new array, taking for each label, I'm going to assign to it the corresponding value. So I can use numpy.choose to do this. So for each label, I'm assigning to it the corresponding value. Does that make sense? Alright, I just need to reshape it because I flattened it. And then I can look at it. There we go. Alright, so we've basically replaced every point of the histogram by its cluster center. So here's the raw image, here is our quantized version, and here is simply by taking equal bins of the histogram, splitting the histogram in 5. Is k-means doing any better than equal bins? That's hard to tell. This is an aesthetic judgment. And this shows the problem often with clustering is that quite often it's really hard to judge the quality of a clustering result unless you know what you're looking for, unless you have a specific application in your mind. So by the way, here is the histogram. Dashed lines are equal bins, and full lines are the separation between the clusters estimated by k-means.
Can you show the code you used to display the image again?
I used matShow. Oh, sorry. I used matShow, and I just took the gray color map. mShow would work too. Right, so we've seen k-means clustering. There are other clustering algorithms in the Scikit. One thing that I like about k-means is it's reasonably fast. It's one of the fastest clustering algorithms. Usually, if you're doing unsupervised learning, it's because you have a lot of unlabeled data. Unlabeled data is cheaper than labeled data, so that's one reason why you might be working with unlabeled data. So quite often you want something reasonably fast. Another approach, so k-means can be seen as a bottom-up approach. It's dividing the data in clusters, which means that if you ask for a lot of clusters, it's going to take a lot of time. I don't have in mind the computational complexity. I think actually it is in the k-means documentation. So all the algorithms should have a notes section in their doc string that contains hopefully useful information. And so we can see that the average complexity is not too bad. It scales only linearly with the number of clusters k. The worst case complexity scales pretty badly with the number of clusters. Another problem when you're asking for a lot of clusters is that you have a lot of local minimums. Basically, your answer is simply going to be random depending on your initialization. And that just tells you that if you have high-dimensional data that you're trying to split in many bins, there are a lot of equivalent ways of doing this. So another algorithm, the word clustering algorithm, is a bottom-up approach. It clusters together. It starts from the data is split, completely split, and it clusters together in a greedy way by simply associating observations. So this is interesting if you want a lot of clusters compared to your data. Suppose you've got 10,000 samples and you want to make 5,000 clusters. Word is going to work fairly well. It's not randomly initiated, so run it twice on the same data will give you the same result. Even though you shouldn't trust too much the answers, because if you add noise to your data, it's going to give you different results. So one thing that's really nice about Word is that as it works by merging together observations, you can constrain this merge. You can say, well, I'm going to allow this observation to be merged only with a set of other observations. And that works really well if you have some natural structure in your data. For instance, if you're working with images. If you're working with images, you may want, if you want, for instance, to extract regions of the image, to merge only one cluster, one voxel with its neighboring voxel, or one pixel with its neighboring pixel. So that's what we call connectivity constraint clustering. So here's an example. So that's Lena, on which we've asked, I think, 30 clusters, and we've constrained the clustering. So let's run this. So the first thing we're going to do is actually to downsample data just so that it runs faster. So we're just adding together slices. Yep.
Is that Ward approach similar to the component network?
So cohonent networks, if I'm right, are self-organizing maps. So I've never looked at them personally, but I think they're fairly different. I mean, what Ward does. So Ward is a special case of hierarchical clustering. So what hierarchical clustering do is they're a greedy algorithm. They know how to compute a distance between two observations or an observation and a group of observations. And they look at all the distances and bang, they merge the two that are closest. On and on and on again.
Do you have control over the metric they're using in any distance?
No. So Ward, so out of all the hierarchical clustering algorithm, Ward tries to minimize a criteria that is similar to k-means. So basically the sum of square distances to the cluster center. And it can be seen as giving a good approximation of the data in a mean square error distance, so in an L2 distance. I'm not sure. So Ward relies on the trick. So okay, our implementation of Ward relies on the trick to avoid recomputing all the squares each time. I'm not sure that trick would work out. Yeah, that trick would not work out with an L1 a distance. It won't work with every distance.
So if you want to do a different measure, you have to drill down deep and change that.
Oh, with the Scikit-learn code, yes. I should point out that actually SciPy has a Ward, so the core SciPy has a Ward clustering algorithm that is actually more versatile and that can use different metrics. Actually, it would be useful to expose it with the same API than the Scikit-learn. It would be useful. We're using it in certain cases. There are certain cases in which it's faster than our algorithm, so then we default to the SciPy algorithm, and there would be some value in saying, well, I can do clustering with other metrics. We would accept that for this. It is true that for people who work with text mining, for instance, like to use L1 distances or Manhattan distances, they work better. So I work a lot with images, so I like L2 distance. So we're creating once again next vector of our downscaled Lena. And then this is the big deal. So we're going to import from feature extraction module, and specifically the image module. So from Scikit-learn the feature extraction the image, we're going to import the grid to graph. Right, so one thing I haven't mentioned so far is that in the Scikit-learn we're not really dealing with data massaging. We're taking X vectors, and it's your problem to get as much information as possible in here. This is, from an application standpoint, this is actually really important. If you're trying to solve a real problem and not just a machine learning problem, you want to do things like filter out noise. You can try and trust your machine learning algorithm to do this. Chances are it won't work. You should try it. So we've put very little feature extraction code in the Scikit because we don't believe a general purpose machine learning package can solve this. We believe specific domain specific packages should solve this. But so there's a bit of text feature extraction and a bit of image feature extraction. Because text and image are fairly general. So a grid to graph, what it does is it takes a size of a grid, so 3D grid and X and Y and Z. By default, LZ is 1, so by default I really have a 2D grid. And it returns a connectivity graph. Who is connected to who? So basically we're transforming an image like this in a graph of which pixel is connected to which. And the order is just the order of the rabble operation. So if I give it the shape of Lena, and I get a graph out of it. So I get a graph out of it. My graph is just a sparse matrix. So it's just the adjacency of the graph, the binary graph, stored as a sparse matrix. And so then I'm going to be able to give this graph, this connectivity graph, which tells which observation is connected to which other observation to my Ward algorithm. And so the reason we use connectivity graphs is that this is very general. When you're doing image, you're like, well, can't I just give it a shape and it's going to figure it out? Well, this enables to work on just about any structure. And you can write your own code to create this graph. Alright, so we have our connectivity graph. So now we're going to create a Ward object using cluster.ward, and we're going to tell it that we want 30 clusters. And during the fit, we're going to get our data, but also our connectivity graph. So it fits. So it's important to see that this graph came from the same image than X. So it's got the same number, it's got the number of vertices of the graph is the number of observations in X. It's fitting. Alright. And then I can just extract the labels. So it's just war.labels, but I'm going to reshape them so that they have the same shape than the original image. And then I can just display them. Alright, I'm just going to change color next. Yeah, so that's what we get. Right, does that make sense to everybody? No. Right. So the value, so this can be seen a bit as a Photoshop magic wand thing. I'm clicking in some place and I'm just each time clustering voxels if they look similar. So the distance is the standard L2 distance between voxels. The reason I'm using connectivity graph is that I'm allowing only neighboring voxels to be merged. So basically we have, so the way it works is it takes all the voxels of the image and looks at the two neighboring voxels that have the closest value. Bang, merge them, and again and again and again until it gets to having only 30 clusters. Because I told it that I wanted 30 clusters, and then it stops. So actually, I'm lying. We actually go all the way up because it was easier to code, and then we cut afterwards. Good. Right? Does that make sense now?
If you tried to create the Grizzy graph using the other clustering that didn't do this merging thing, that thing would look totally different.
Correct. The fact that I've put in connectivity constraints means that I'm extracting continuous batches of the image, which can be useful. You may want this, or you may not want this, depending on your application. But for instance, if you're doing prediction on images, and which is what we're going to see right afterwards, and are trying to reduce the dimensionality of your image, chances are you want this spatial constraint, because chances are your features, that your relevant features in the image are going to be located in a neighborhood, in a physical neighborhood. So you don't want to do clustering on a histogram only basis. You want to be clustering on a histogram and structure basis. But that really depends on your application. Another nice thing is that it actually speeds up the word clustering algorithm a lot, because you've got less comparisons. So I do this on brain images that are, I think I have 50,000 voxels, and I have 800 observations. Or I have 20,000 observations. Takes 20 seconds. But that works only because they're a 3D image, and adding the connectivity constraint has just reduced the number of comparisons to do by a huge amount. Right, feature agglomeration. That's just dwelling on the same idea. So if we think of our digits data set, it's made of a set of images. So up to now, we have been considering that the voxel on the image was the random value. Each voxel was seen as an observation of a process, and we're trying to do clustering on it. Now, if I'm actually trying to do learning from on images, then voxels are my features. But I still may want to cluster them. If I have really big images and I think that actually the voxels are just conveying the same information, I may want to cluster them. So one way to do this would simply be to take my water algorithm and transpose the data, put it in, transpose back. We actually have an object to do this that we call feature agglomeration object. And so one way, so on the digits data set, one way to see this is that I've got all these images of digits. I'm going to look at those that have pretty much the same the same values across the different digits, and I'm going to cluster them. And this will allow me to reduce a bit the dimensionality of my data. So this is, for instance, the original data. And this is, so I've learned this clustering across all images. And this is the agglomerated data. And this is for 30 or 32 clusters. And we can see that we're losing information. For instance, here the little white pixel here that's really important to figure out it's a 1 has been a bit smoothed out because the cluster was of size non-zero here. So it's a trade-off. We're losing information, but we're reducing the dimensionality of the data set. On this example, on the digit example, it's a bad example. The images are too small. If we had really big images, for instance, that have been taken by a blurry camera that blurs out the data, clustering would be great because of the blurring, there is not the two voxels, 2 pixels are not independent. They're heavily correlated. On the digit data set, it actually doesn't improve prediction, but we can still try it out. So
Gael, is it true in practice, in your work, do you sort of impose a blurring by convolving the image with it?
Oh, that's an interesting question. So that's getting a bit too much in my application. So there are 2 reasons the images are blurred in my work. One is that the images come from a MRI scanner. The MRI scanner has a finite point spread function, so basically point source is going to give a blurry Gaussian-like image. The other one is that it has basically speckle-like noise. So if I blur, if I convolve, I'm going to reduce the noise and so increase the signal to noise. So this is one way of doing it. It's actually, you can actually do better by actually doing an estimator that knows that things are correlated and doesn't do blurring, but tries to find information on the corresponding grid. This is way beyond this tutorial. But actually, so the fancy estimator works better and takes much more time. This feature agglomeration works slightly less well and is super fast. So to do feature agglomeration on the digits data set, we can create a connectivity matrix that is created from only one image, because it's really the connectivity of one image that we want to impose. And then this time our X data set is 2D. It's the standard X data set from digits. So it's 1800 observation of a 64 size data set. And we can fit it. So I am going to run this example. So connectivity matrix is a 64 by 64 matrix. It tells me which voxel of the image is connected to which other voxel. So I'm going to use the word agglomeration object, and I'm going to give it the connectivity matrix. And I'm going to tell it that I want 32 clusters. This object I can fit on the data. No, I need to call this fit method. And the nice thing is I can use it to transform the data. So this object exposes a transform method. And it's going to give me a smaller data set. A data set that has less features because we've merged together features. I can also transform this back to a restored data set. So taking the reduced dimension and just basically assigning the value to each cluster label. So that's just an inverse transform. And this data set has the same shape as the original one, but actually has less information because it's been through a compression or approximation and back up. Alright, so maybe order enumeration may not be useful depends on what you do. What's interesting to see here is to see that if you've got a massive amount of data, unsupervised methods can be used to transform and reduce the amount of data. Though, as I said, they know nothing of what you're trying to predict. And here they've forgotten something that's probably a very important feature. They've blurred it out. So, got to be careful with them. They might not help you. They do simplify the problem. Another case where they might be really useful is if you've got a massive amount of unlabeled data and a small amount of labeled data. So you can run the unsupervised to learn the data reduction on all your data, and then run the supervised on your labeled data. All right.
So, could you implement a stopping rule for the number of clusters?
No, that's an excellent question. And so what we've actually done is a bit more fancy than this, but we've done what we call a supervised clustering that does something like this. I mean, basically, it's a bit more clever than this. So you've got a tree of association, and then we just deconstruct the tree by looking at what cut predicts better.
So you do it visually, or?
Oh no! I don't do anything visually. So basically, in statistics, there are two kinds of people: those who trust a user looking at a graph, and those who want a hard model-selection criteria. I'm in the hard model-selection criteria. If I give to neuroscientists, I work with neuroscientists. If I give them a choice to make visually, they're going to take the choice that gives the answer they want.
So this is in the Scikit?
No, this is not. It's actually. We're actually, right now I have a student that's working on making it open source, but it's going to be in a neuroimaging package. But it's really going to be taking X and Y data sets, so you could just grab it. It's really interesting in the kind of data I have because it's heavily locally correlated. It might not be, depending on your application. I mean, I have super high dimensional data that are heavily locally correlated. But yeah, I mean, it's going to be available on. Look on my GitHub page, there's going to be a fork of the project. Well, it is already there. Okay, so we've seen clustering. We can look at what we call decomposition problems. So the idea is that we're going to be looking at changing the observation basis. If I've three variables, and the third one is given by the sum of the two other ones, and maybe a bit of observation noise. The third one is giving me no information whatsoever. So we actually want to get rid of this one. What's that?
Wherever there's overlap.
Some kind of overlap. So one way of looking at this is through principal component analysis. So here's a bit of a 3D plot. So we've got three variables. They're a cloud of points. And by looking at them, at least looking at a projection, it's hard to see their structure. But I've run on them PCA, principal component analysis, which is going to try to find the direction, so the loading of variables, that explains the maximum amount of variance. Find one, it's actually this one. And then it finds the orthogonal one that explains the maximum amount of remaining variance, and again and again and again. So if we look at that, we can see that basically this data was pretty much flat. If we, but we can see this only if we look at it in this basis. So I've got a set of orthogonal vectors, and by looking at it in this basis, I can see this data is flat. So another way of saying this is that the amount of explained variance at some point gets pretty much to zero. I've got directions that don't explain any variance. So chances are I want to throw them away. But once again, chances are it might be that if I have a classification problem, the difference between my two classes is lying in this direction. So this is exactly what I'm doing here, and I'm going to speed along a bit. It's getting late. But I've created two random variables. A third one that's the sum of the two others. It brings no information. So that's a 3D data set. I create a PCA object, so importing from a Scikit-learn decomposition. I fit it to the data. Then I look at the amount of explained variance. And I can see that the two first directions explain some variance, and the last one just explains nothing. This is numerical error. So, I mean, if I'm down to this, I can throw away this last component. So I can tell my PCA algorithm that I want two components. So I just tell I want two components. And here I'm introducing a new method that's fit transform. So fit transform does exactly the same thing as doing fit, then afterwards transform. It's just an uncertain algorithm like the PCA, it's quicker. So you're going to get the same results, might be quicker. So basically I'm reducing the dimensionality to something. I was about to say to these two variables, but no, I'm not guaranteed I'm going to get these two variables. I get the same amount of information.
What if you had 3 linear combinations rather than just the third one? Would it still find the two?
Yeah,
Find
no, that's
dimensions that space?
yeah, that's no problem. Problem more is that what if I had my third variable that was the square of my first variable? That wouldn't work. That's a linear model. Another problem is that in real life you never have this. You never have 0 here. So then the question is, where do you cut? I just said I don't like to have meter parameters that were selected visually. Honestly, there's no good answer for this. We can come up with models. I can have Bayesian prior on the number of components. There have been papers written on this. On real data, it works only if your data has the same hypothesis that in the paper. This is actually a problem I really do not know how to solve. Just like choosing the number of clusters. Yeah.
In the case where the data, like the digits one, isn't a real number, it's like a 0 or a 1 type data, can you still use this type of approach?
Well, the fact that it's real numbers is not a big deal because you can see real numbers as an approximation of the continuous numbers. If you had only zeros and ones, for instance, that'd be a bit ugly. You could, but it wouldn't work too well.
I don't know if it's valid if you have the data that's naturally binary. If you produce a decomposition that is flowing for numbers, I'm not sure. Something got lost there. I'm not sure where that went.
Well, valid. Something is valid only if you're trying to do inference with it. I mean, you can do invalid things only if you draw conclusions. If you're just using this as a black box prediction framework, then if you're careful not to mix your training and your test data sets, then it's valid. The question is, how are your conclusions going to be valid? All right. Any other questions in PCA? That's a very, very, very used data reduction setting. So actually one good way of setting the number of components was if you have a supervised problem, you could just vary the number of components to get the best prediction. That I would buy. If I'm reading an article and you're telling me I'm setting the number of components to maximize prediction, I buy. If you're telling me I'm setting the number of components because I know there are that number of neurons in the brain and blah, 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 I don't buy. Depends on your nodes. All right, independent component analysis. So same kind of idea. I'm going to try to find directions in my data that are interesting, except I'm not going to be looking at explained variance. The idea being that I'm going to try to find variables that are maximally independent, and over-interpretation creeps in. People start making conclusions about how they found an independent variable. Don't find an independent variable. Sorry for the typos, by the way. But under certain assumptions, you can recover some signals. And this is an example where it works well. So it works well for heavily non-Gaussian variables. So for instance, here we have, on the one side, we have a noisy square function. So this is heavily non-Gaussian. I mean, it's almost binary. It's sitting on one side, sitting on the other side. And on the other side, we've got a sine, which is non-Gaussian, but more Gaussian. And so if we mix them together by randomly combining them, so if we run PCE on them, it's not going to be able to separate at all. It's just going to look at, find the loading that has the maximum amount of energy. But if you run RC on it, it actually works really well here. And this works because the variables are non-Gaussian. So I'm not going to type this code, but basically here we're just generating the data. And adding a bit of noise. And here we're creating a random mixing matrix. Oh, we're standardizing the data. We're creating a random mixing matrix, so just randomly mixing. Actually, it's not random, but it could be. We're running the fast ICA, so fast ICA is an implementation of the data. So once again, we have fit and we have transform. And we're just checking that we can get a similar mixing matrix than what we've put in our data. You've got fairly little guarantees of recovery in this. All right, any questions on ICA?
Actually, this as k-means. If you look at k-means, when you do your k-means clustering, do you actually get like centroids? Say you want to maybe say plot it on a XY scale. Can you actually get the centroid locations and the distances of the items that are clustered around the centroid?
The centering locations are cluster center on the score. So that's the cluster centers. The distances, you can either compute them. We're not storing the distances. You could compute them. Actually, the best example for something like this is try to have a look at the source code. We're really striving to have it easily readable, and you'll find that, of course, in the source code during the algorithm is computing the distance. So you already have the function to compute the distance. It's in there. So try to have a look at the source code. And we're really fighting to have a highly readable source code. And same thing, I mean, we're fighting to have good documentation. I think it's pretty decent, but it's going to be an evil. Look at the source code. Hopefully it's readable. All right. So there are other decomposition methods. We're going to have even more. We've got Google Summer of Code student working on that. So we're going to have things like sparse PCA. We have non-negative matrix factorization. Just like everything, I mean, there is a zoology of these objects. In the Scikit, we have, I should bring up the white page of the Scikit. We're trying really hard to have a lot of figures and examples. So, oh, by the way, this is Gaussian processes. So fairly similar to what Chris presented this morning. So we try really to have a huge amount of examples, to have text going with them, to explain these examples, to have, so this is a clustering algorithm with the centroids, to have figures to try to help you develop an intuitive feeling about this, to have C also, to have discussion about the links between the different algorithms. We can't give a simple message. We can't tell you, oh, just use this method, it's going to solve all your problems. This is untrue, and you're going to have to try out different methods and understand a bit what's in your data. We do try to make it as easy as possible to do this. All right, so we've got half an hour left. Everybody's really tired. So I'm going to introduce one more concept, and then we're going to do a bit of fancy examples, just to have fun. So pipelining, and I need to You guys want to take a 5 minute break? Yeah.
Yeah.